Hey everybody, and welcome to the first video of Chapter 3. Now, Chapter 3 is all about interest rates and calculating and optimizing rates of return. However, today, to set up the rest of the chapter, we're going to talk about some very basics about what interest rates are and then how we calculate present and future values. So just as an overview, we're going to get to the very basic level and talk about what interest rates are and why we charge them. And then we're going to talk about compounding and discounting interest rates. So why charge interest in the first place? Well, there are three main reasons that we want to charge interest. The first, if you remember back to chapter 2, is that inflation rates are likely going to be greater than zero. And so with that, that means that a dollar today is not going to be able to buy as much stuff as a dollar tomorrow. So when I invest $1 as a loan, when I get that dollar back, it's probably going to be worth less than that. And to make up for that difference in value, we charge interest. The second reason is because the chance of defaulting is always greater than zero. It doesn't matter how trustworthy the friend is that you're lending money to, or the company, or even the US government. There will always be some chance of default. And because there's a chance of default, there's a chance that the loan never gets paid back. So it is a risky investment. And to make up for that added risk that you're taking on as a lender, you charge interest as a way to account for a risk premium so that it is worth your time to take on that added risk. Now, the final reason is a little less talked about, but it's still important, is that there's a lost opportunity cost when you give out a loan. If I lend $100 to my friend and he's going to pay me back next month, I lose the ability to buy stuff with that $100 while my friend gains the ability to use that $100. Therefore, there's some opportunity cost where I could have invested with something else. And to make up for that opportunity cost, my friend is going to give me some interest to pay me for that opportunity cost being lost. Now, as we move into the compounding and discounting topics, let's set up a very easy motivational example. Let's look at loan A and loan B in front of us. These are two sample auto loans. The first one pays us $366.19 a month for 48 months. The second one pays $318.71 a month, but for 60 months. If you were a bank, which would you rather loan out, A or B? It's hard to tell the difference with just looking at it like this because while loan A pays us more per month, it lasts less amount of time. Whereas with loan B, it pays less, but there's an extra year of payments. And so as a bank, you need a way to compare these loans to figure out which is the better investment. And we do that by calculating the future value of a loan. The future value is what we're trying to maximize as an investor. It is the value at some future date of an investment that is made today. So let's just go with a very basic, easy example in front of us. Let's say that there's a $1,000 principal loan that charges 5% interest and has a 1 year time to maturity. Let's try and figure out how much money we will get at the end of the following year when we get paid the money back. And we can do that with equation 1. So the future value at the end of 1 year, hence the subscript 1, is equal to the principal times 1 plus the interest rate. And note that the interest rate I is always going to be calculated using the decimal form of the interest rate percentage. So it should always be a decimal as you look in the second line here. In this case, the future value after 1 year is $1,000 times 1 plus 0.05, or $1,050. In other words, without $1,000 principal loan will pay us back $1,050 next year. But most loans don't have a perfect 1 year maturity date, and that's where the topic of compounding interest comes in. Compounding is just the process of earning interest on the principal investment and on the interest earned as savings accumulate over time. So let's go to example 2, which builds off of the previous one. We're going to assume once again that there's a $1,000 principal loan with 5% interest and 2-year time to maturity. But we're going to say that this is a compounding loan. In other words, that on the second year of the loan, they have to pay interest on the interest that we gained in the first year. We can calculate it actually pretty easily using equation 1. We already know what the future value after year 1 is, and then all that we're going to do is we're just going to add 5% interest to that. So future value after 1 year times 1 plus 0.05. And that gets us to the future value in year 2. But that can get a little bit messy to calculate, and so we can do a little bit of math to rearrange this equation and get this nice line right here, where we get the principal times 1 plus the interest rate squared to denote 2 years, as you can see from the middle line of the equation. And so the future value after 2 years of this compounding loan is $1,000, the principal investment, times 1 plus 0.05 squared, or $1,102.50. Pretty cool, right? Notice a couple things. First off, even though we made $50 of interest in the first year, the second year made $52.50. And that is because we got interest at 5% on that $50 as well as the $1,000 principal investment. And that's a really important fact for later on, because this is an extremely generalizable result. The future value for any number of periods is equal to the principal times 1 plus I raised to that number of periods. So if we're looking at a 10-year loan, it compounds annually, and it'll be 10. And this has some really cool mathematical implications. If you look at the graph below, this just uses our same example and extends it out to 45-year time horizon. So if you look at the intercept, it intercepts at 1,000. And if we had jumped out 1 year, this would be 1,050. Jumped out 2 years, it goes to $1,102.50. But as we expand the time horizon, you see that this starts to grow exponentially, where at the end of 45 years, this is worth, that one loan is worth over $9,000. And in one of the supplemental videos, we're going to talk about implications to this with retirement savings, specifically why it's important for us to talk about our retirement even though we're all really young. And that's all because of this exponential pattern. But now let's look at the flip side of this. What if we're, let's say, trying to set a target? Let's say that we're trying to save money by putting it in the bank and earning interest on it to get to a target future value. Well, then we just have to rearrange equation 3 to get equation 4. You guys should recognize the future value at a select time length n is equal to the principal, or the present value, which we're trying to solve for in this case, times 1 plus the interest rate raised to the number of periods. We can solve for the present value by just dividing the second term to get this. And we can do a little bit of comparative statics on equation 4. If the math behind this is a bit confusing for you guys, please talk to me, but I'm assuming that you at least understand basic fractions and derivatives since you are in this class, the senior level class. First is that the present value is decreasing in n. So in other words, as n increases, the present value decreases, which is a result that we learned from that last picture. If you want to save $1,000 in 10 years, you need to invest less money than if you're trying to get it in 5 years. The next one is that the present value is decreasing in I. So in other words, as you gain less interest, you need to increase the amount of money that you invest initially. And then finally, the present value is increasing in the future value, which is a pretty logical conclusion. That just says that the more you want to make in the future, the more you want to invest initially. And so let's just look at a couple of this nice table here that looks at the present value of a $1,000 payment to be received in different periods of time and with different interest rates. As you can see, If you were charged 20% interest and you want $1,000 in 30 years, you only need to invest $4.21. Now, most Roth IRAs only give you a return of about at most 10%. But in 30 years, $1,000 you only need to get by investing 57, even at a 10% interest rate. However, to get it in 15 years, you need to invest $239.39. And so we can really take out of this one big concept that the price of a financial asset is equal to the present value of the payments to be received from owning it. And this is a big theme that we're going to take from this slide and video to all the rest in this chapter.